All right, welcome everyone to another meeting of Symmetries in Newcastle. The first speaker of today is Claudio Bravo from University of Chile, and he'll be talking about quotients of Bruhat-Tits tree by function field analogs of the Hecke Congruence subgroups.
Thank you very much, Michael, for the presentation, and also thank you very much for the opportunity. In this presentation, I will expose the principal results of my PhD thesis. So the structure is the following. The structure of the presentation is the following. I will start by present some preliminaries which are necessary in order to understand the main result. Then we can do a sketch of proof of the main results. And by applying this, we can describe the amalgamated product of some interesting group, of some arithmetic group that interest you, which act on trees. And finally, we present some examples, and we pass for do some commentaries about some generalization of this work. So we can start by the preliminaries. So as the title of this talk indicates, here we study the action of certain arithmetic subgroups on the Bruhat-Tits tree. So in order to understand this, let's to introduce this concept, the Bruhat-Tits tree. So in order to do this, let F be a field with a discrete valuation map. When we have this type of field, then we can naturally define the ring of integers here as the set of elements whose valuation is positive or 0. And we can also fix an uniformizing parameter as an element whose valuation equals 1. So we have this local definition, and also by using this local structure, we can define orders here as all lattices with our ring structure derived from the multiplication in M to F. And then we can define the vertex set of the Bruhat-Tits tree as the set of such maximal orders, all contained in M to F. And they are maximal with respect to the natural relation defined by the inclusion. Or equivalently, we can define it. We can define them as a set of endomorphism of local lattices of rank 2. So we have the vertex set of this graph, of the graph called the Bruhat-Tits tree. Now we want to explore, or we want to understand the structure of edges. And in order to define this, we define this relation, the relation of neighboring vertices, as the following. We say that two vertices are neighborhoods precisely when they satisfy this relation. The quotient of D by the intersection is isomorphic to the residue field. So we have a graph, and this graph is in fact a tree. We can see this, for example, in the books in the book of tree due to Bass-Serre, and we have a tree like this. This is a regular tree in the sense that the valency of any vertex is the same. And here we have edges, and when we collect a finite number of edges of consecutive edges without backtracking, then we have a finite path. And when we pass to the limit on one direction, for example, we can define rates here, and we have this type of subtrees. And in the picture, we can see the Bruhat-Tits tree of SL2, where the ground field is F2. Since it is well known that the number of elements in the start of a given vertex is parameterized by P1 K, where K is the residue field. Okay, So as we said above, we can define rays here, and on the set of rays, we can also define an equivalence relation as follows. We say that two rays have the same visual limits when they contain a common subray. So this is a general definition, and in the case of the Bruhat-Tits tree, we can see that the set of such visual limit is parameterized by P1F. In other words, this is parameterized by F union infinity. So we have here two natural actions. On one hand, the group of invertible matrices acts on the set of maximal order by conjugation, and this action respects the neighborhooding relation. So we have an action of the invertible matrices on the Bruhat-Tits tree. We have this on one hand, and on the other hand, we have the action of GL2F on P1 by Möbius transformation. So this is a very natural question if these actions are compatible, and the answer is yes. This action is totally compatible. We can see this in the book of on the book titled Trees due to Jean-Pierre Serre, for example. Okay, we have this type of actions. And now, in order to introduce our main goal, let's use to introduce some additional concepts. So let's see the projective smooth geometrical integral curve defined over a finite field F. Here, the hypothesis that says that F is finite is very important, since we work with the genus theory, which only works in the context of finite field. So this is important. So when we have a projective curve, then we can define the global field K as the function field of C, and then we can also fix a closed point on the curve. So the closed point on the curve C define a discrete valuation on the global field K. And this is a well-known result. So we have a field with a discrete valuation map, and then we can define a Bruhat-Tits tree as above. Okay, we have this on one hand, the definition of the Bruhat-Tits tree here. But on the other hand, we have to fix some other notation in order to expose our main goal. And we do this as follows. So let D be a divisor on the curve, and let's use the node by LD, the line bundle, the natural line bundle defined from the preceding divisor. This is defined on or at any open sets by this relation. This is the most natural form to define a line bundle from a divisor. And it fixes an isomorphism between linear equivalence on divisor and line bundles, for example, or class homotopes of line bundles. I don't remember all the details. So we have this, and by using the preceding line bundle, we can define the following sheaf. We denote by D sub D the sheaf on OSE algebras defined by this relation. This is a maximal order in some sense, by using some definitions. And then we can define E sub D as the intersection of the following sheaf, the sheaf D sub D, with the sheaf D sub 0. This is the intersection in the sense of sheaf. So if we denote by U0 the following affine open set, the affine open set defined as the curve by forgetting the point at infinity by infinity, and if we denote by R the ring of functions that are regular in U0 or outside the infinity, then the group of invertible matrices in the U0 section of D sub D equals this. This is a direct, we can see this by a direct compute. And this set of matrices is the set of invertible matrices that are upper triangular when we pass to the quotient for some ideals, and the ideal is this. So we can directly see here that the group HD is a natural analog to the Hecke Congruence group in the context of function fields. So this is a very natural goal to characterize the action of HD on the Bruhat-Tits tree, and more specifically to understand the associated quotient graph here. Why we can do the following question? Why this is a very natural question, and we can cite the following example in order to explain this. For example, we can fix the divisor, and we can say that the divisor equals 0, and in this context, the preceding objective reduces to the following two theorems due to Bass-Serre in the book of trees. So in this context, we have that the associated quotient graph is combinatorially finite. In other words, it is obtained by attaching a finite number of rays called cuspidal rays to a certain finite graph way. And moreover, the set of such cuspidal rays is indexed by the element in the apical root of the ring R. Okay, and this identifies with this. Here we have some commentaries. For one is the following. We can see, for example, that if we have a cuspidal ray, then a subray of such cuspidal ray is also a cuspidal ray. So here, when we count the number of cuspidal ray, the possible subrays that are redundant are avoided. This is one commentary, and the other is a full set of non-redundant cuspidal rays is called a cuspidal set, and the number of elements here is called the cusp number of the associated combinatorial finite graph. So we have this, and by using this description of the on the graph, Bass-Serre can do the following theorem on the structure of the group that acts on the tree by using the Bass-Serre theory. He says that there exists a finitely generated group H and a family of triples where E sigma is an error fractional ideal. P sigma is isomorphic to a group of upper triangular matrices where the eigenvalues belong to F, belong to the ground field, and the unipotent pair is parameterized by the preceding ideal. And also there exist groups with canonical injection to H and all P sigma, all the group P sigma, such that GL2R is isomorphic to the summa or is isomorphic to the free product of the preceding P sigma, parameterized by the Picar group, and H amalgamated along the common subgroup P sigma, according to the canonical injection defined above. So this description on the group GL2R is very important. Or it has some important consequences on the homology and cohomology of such groups. For example, we can deduce it by using the spectral sequence defined from the action on GL2 of GL2 on the Bruhat-Tits tree, or by using the Mayer-Vittery's exact sequence defined from the preceding description as an amalgamated product. So this type of theorem applies to homology and cohomology, for example. So we have the following theorems that which are analog to the Serre theorem, and they describe the action of the Hecke Congruence subgroup on the Bruhat-Tits tree. So let's D be an effective divisor, which we write in the canonical form, where the point P1 and Pr and P infinity are all different. Then the associated quotient graph is combinatorial finite. This is the first part of the theorem. This is not hard to deduce, in fact. But the other part is more interesting, since we can deduce that the cusp number of the preceding combinatorial finite graph satisfies the following relation. This is bounded by this expression, where G2 is the maximal exponent to subgroup of the Picard group. So, and moreover, equality holds when G2 is trivial and H and E is odd. So we can see here, for example, that the number of cusps increases when the Picard group is more complicated, or also that the cusp number of the preceding graph increases when the divisor is more complicated, when the multiplicity is bigger. So we have this theorem on the associated quotient graph, and then we can pass to the description of the associated group. So here we assume that H and E is odd and G2 is trivial, and in this context there exists a finitely generated subgroup, like in the Serre theorem. But here there exists two sets of indices, D and A, and a family of triples indexed by the disjoint union of the preceding one, where the cardinality of D equals this, and the cardinality of A equals to the complementary. This the set of cuspidal ray minus the set of the preceding set, where E sigma is an R ideal again, and where we have a little difference with the here we have a little difference with the Serre theorem, since in the case where D belongs to D, then we have the same group as in the Serre context. So we have a group which is homomorphic to a set of upper triangular matrices where the eigenvalues belong to F star, and they can be different or not. But when sigma belongs to A, then the eigenvalues of the preceding elements in the group are the same, and then we do not have a semi-direct product. We have a direct product indeed. And also we have a group with canonical injection to H and HP sigma, such that the Hecke Congruence subgroup is homomorphic to the sum of P sigma and H amalgamated along the common subgroup, as above, as in the context of Serre. So here we have two indices and two type of group P sigma, which describe the combinatorial structure of the Hecke Congruence subgroup. Moreover, we have the following theorem, which allow the description of the homology with coefficient in zeta in the ring of integers, since we have the following. We can describe the abelianization of the Hecke Congruence subgroup, since the abelianization is H1. H1 with coefficient in the integral ring. And we can say that this group, the group of the abelianization of the Hecke Congruence subgroup is finitely generated if H and E equals 1, or is the product of a finitely generated group with an infinite dimensional FP vector space in any other case. So we have the case of finitely generated group are not finitely generated group. This is the idea. And this is classified by the coefficient N and E. So now we can pass to the proof of the main result. Okay. A problem? No. Okay. But here, in order to give a sketch of the proof of the preceding result, we need to use the theory of genus, which follows from another area of algebra, from the quadratic forms, indeed. And in order to introduce this theory, we need to define orders in general. So let's R via the order of maximal rank. In other words, R is a locally free sheaf in OC algebras whose generic fiber is M2K. We say that R prime belongs to the same genus of R if for any place we have that the local orders are GL2KP conjugated, or which is the same, that they are adelically conjugated. So the following is a fact which follows from the how do you say that, from the well okay, I don't remember the theory, the class field theory. So sorry, which follows from the class field theory. And the fact is the following: given a genus, we can define a class field by using the norm of the adelic matrix stabilizing the order R. And moreover, there exists a distance map which takes values in the Galois group of the preceding extension. So we have this, and let's introduce some additional concepts. An Eichler C-order of level D is the intersection of two maximal C-orders. In other words, two maximal orders of maximal rank that are maximal with respect to the inclusion, such that D equals to the sum of dP multiplying P, where dP is the distance in the Bruhat-Tits tree between the preceding, between the associated local maximal orders. So this is the set of level D Eichler C orders, and the following is a fact. It is not hard to show, but I don't want to recall it. It's here. The set of Eichler C orders of level D is a genus, and we will denote it by O sub D. So now, we have the following problem in order to prove theorem 1. I will recall it. So this is the theorem 1. The problem here is that HD, the Hecke Congruence group, fails to be normal in GL2R, for instance, and for this reason we do not have a direct computation of this number of cuspid array. So we need to pass for an auxiliary quotient graph, and this auxiliary quotient graph is the classifying graph. So the classifying graph can be defined as follows. Let Q be a closed point, see, that is not contained into support of the divisor. Then for each Eichler order of level D, or for each element in genus O sub D, we define the individual C-graph, the C-graph CQ defined from the preceding Eichler order as the quotient graph defined associated to the action of the normalizer of the U0 section of the section of say minus Q of the preceding Eichler order. So we have this graph. We can think that we can see think this quotient graph as the quotient by some normalizer, so group that is bigger than the invertible part, the invertible matrices. But in order to define the full classifying graph, we have to do the following. We say that two Eichler orders are equivalent when the image by the distant map between the preceding pair belongs to the group generated by this, generated by the uniformizing parameter at Q in the Galois group by the preceding machinery, by this machinery. So this is an equivalent relation, and then we can fix a representative system defined from the preceding relation, and the full classifying graph is defined as the disjoint union of the preceding C-graph corresponding to the orders in the preceding set of representative elements. So we have this, and this is the classifying graph. Some disjoint union of quotient of the Bruhat-Tits tree by normalizers. So the following proposition I'll use to understand or I'll use to prove the theorem 1 in the following form. So proposition 1 says that the cusp number of any connected component of the classifying graphs is the same. And this number equals this, say D, which is the multiplication of alpha D with this index, where alpha D is this, and where pay A1 and pay AU are the closed points in C whose coefficients in the divisor are odd. We have this, and we have the following lemma. We believe that this lemma does not surprise to expert in the area, but we need this in order to prove theorem 1. So recall that the Serre result showed that the cusp number defined from the action of GL2R on the Bruhat-Tits tree is parameterized by this quotient. Another question here is how to expand this theorem to subgroups, and the answer for this question is the following. Let H be a discrete subgroup of GL2R that is commensurable with GL2R. Then the set of cusp defined from the action of H on T is parameterized by the quotient of H on P1. Or this is the same that the quotient of H on the visual limit of the tree. Okay, we have this. And now by using proposition 1 and the preceding lemma, we can do a sketch of proof of theorem 1. So let gamma be the normalizer of the U0 section of the Eichler order AD. defined as in the first part of this exposition. So it follows from proposition one that this quotient, the quotient by the normalizer, has exactly say sub d cusp by proposition one. So on the other hand, by using this theorem, due to Luis Arenas Carmona, which is my PhD advisor, and also describing the Galois group, this Galois group, the Galois group of defined from the genus of Eichler orders in terms of the picker group, then we prove that the index between gamma and HD equal this. So since the cusp number of the graph, the graph defined from the action of Hecke Congruence subgroup is parameterized by this, it follows from the preceding lemma. It cannot accept this multiplication. So the inequality in turn one follows by just multiplying both parts. And the second part of term one, the equality, follows from the next lemma. So if we assume that each NE is odd and G2 is trivial, then we have exactly the index cusp with the same image in the quotient by the normalizer. So in this context, we have the equality. And then we have this sketch of proof. But here we can see that we have reduces theorem one to proposition one. So the next step is to prove proposition one. In order to do this, we define this concept, the concept of reads. We will do this in the following 5 slices. So we can begin by the following concept. A local Eichler order is the intersection of two maximal orders. This is the same. This is a direct analog of the Eichler or of the global Eichler order defined above. Then the set of maximal order containing a local Eichler order form a finite path on in the Bruhat-Tits tree. So we can collect this finite path in a product and define by using this concrete degree. So given an Eichler C order of level D, then we define the concrete degree associated to the preceding Eichler order as this product, the product of all the finite paths containing the local maximal order containing AP. Here we see this product in an infinite product of Bruhat-Tits tree, but since two maximal rank orders are the same at almost all places, it follows from the global local properties, then we can see that this product is indeed finite. This is a product on a finite number of places. Since in almost all places, the maximal order that define the preceding Eichler order coincides. So we have this. This is the description of the grid, and we have grids are very useful since we have the following proposition. Just before this, let's introduce the following observation. The group GL2K acts on the set of concrete degrees, and the orbits are called the abstract degrees. And the proposition says that the abstract degrees index the vertices in the classifying graph in the following form. The vertices in the classifying graph are in bijection with the abstract degrees, while the geometrically edges are in bijection with the D plus Q grids. So we just have to explore the form, or we just to study the preceding rates. And in order to do this, we define the concept of semi-decomposition datum. So if we fix a concrete degree, a semi-decomposition datum of the preceding concrete degree is a tuple where beta is a basis and A sub beta is the base change matrices between the canonical matrices to beta. B and D prime are two divisors satisfying this relation. It says that at any coordinate, D prime contains at least the middle part. Also, there exists a corner which has this form, and the preceding concrete grid contains a subgrid whose vertices are this. They have the same form as the corner, but the divisor which index the middle part satisfy this relation. So they are at any component of the product, they are the middle part or more. And no other vertex, no vertex outside this subgrid is split in base beta. And also, if D prime equals D, then the semi-decomposition datum is called a totally decomposition datum, since they decompose all the vertex at the same time. So the preceding theorem is one of the most important theorem in this work. It says that for almost every abstract grid and representative here, there exists a semi-decomposition datum. Moreover, D prime is unique, and the class of B, the image of the class of B in the Picard group is unique. Now, by using this theorem, we can prove proposition 1. So let's map the BS be an abstract grid, and we can define its corner as the zero subgrid, defined like as in this expression. This is the corner. This is the corner defined from the point C. So we define this morphism, the morphism from the classifying graph defined from Eichler C orders to the classifying graph of maximal orders by using the preceding function. Here we take a grid, we associate it the zero corner, the corner zero grid. So this function is a regular covering on cuspidal array. We can prove it without any problem. And we have the following proposition. If we denote alpha D in order to denote this expression, then we have that the following. We can count the number of pre-image of a given class of maximal orders. And then we can count the number of leaf of the preceding covering. So let's B be a divisor whose degree is greater than the degree of D, and assume that this is not contained in the image of vertex in some bath part. Then the number of pre-image of D sub D is exactly alpha D. So by using this, we can deduce proposition 1, since the number of cusp of the classifying graph of maximal orders is exactly the cardinality of the Piker group. We can prove it. We can prove it by using some tools at some work of Luis Arenas Carmona. And then we deduce from the preceding proposition that then the cusp number of the classifying graph of Euler orders is the multiplication of the Piker group with alpha t. And a more detailed compute shows that the cusp number is the same for any components, and it computes explicitly. So this is the proof of proposition 1, and finally this proof theorem 1 by using grids and this type of tools. Now we want to explore a proof for theorem 2 and 3, and this is so direct now. We say that a cuspidal array in the quotient by the Hecke Congruence group is split if its image in the classifying graph only contains vertices corresponding to grids, to the grids with a total decomposition datum. This is it's a definition, but we can do the following. We leave H cuspidal array to array in the Bruhat-Tits tree where the visual limit of the preceding ray is different than the infinity. Then, if we write if we write V sub n of chi in order to denote a vertex in this ray, and we assume that these two vertices are neighborhoods, then we have the following description of the vertex stabilizers. So let's A sub d, the R ideal defined by this expression. Let Rn, the set of elements in R whose valuation is bigger than minus n. When we take the polynomial ring here, we see polynomials whose degree is bounded. And let Qg be this intersection of ideals when E is invertible, while Q0 equals R. Then the vertex stabilizer equals this subgroup, the set of upper triangular, this is isomorphic to the set of upper triangular matrices where eigenvalues belongs to F star, when the leaf of the preceding cuspidal array is a split cuspidal array. It's a split by using this definition. And in any other case, we have this description for the vertex stabilizer. So theorem 2 reduces to use or to apply Bass-Serre theory for the action of HD on T and use the preceding lemma. And naturally, theorem 3 follows from the description of the homology group by theorem 2, by using theorem 2. So this is this is a sketch of the proof of the main result here. And now we have some interesting examples. The first one is the following: when the curve is the line, the projective line, and when we fix P infinity as the point at infinity here, then we have that are equals to the polynomial ring, and then we can fix D equals to the divisor of T. In this context, the associated quotient graph is isomorphic to a double ray or to a maximal path. Moreover, HD is isomorphic to the product of this following two graphs. We can identify this as the set of upper triangular matrices where the unipotent part is indexed by the polynomial ring. This we can identify this as the set of lower triangular matrices where the unipotent part is indexed by this ideal, the ideal generated by T. And we have to amalgamate the preceding group by the intersection between these groups. So we have this example, and when we take the curve equals to P1, the projective line defined over F2, and R as above, and when we fix D equals to the divisor of T multiplying T plus 1, then the associated quotient graph is isomorphic to the union of 4 rays. Moreover, in this context, we have a free product. HD is isomorphic to the free product of 4 copies of the polynomial ring. Since the quotient graph is a tree, and also the stabilizer of the intersection is trivial. So the Bass-Serre theory says that we have a free product. And it's very well. This is very. This is not. Generally, we do not have this type of examples of products for the amalgamated product. So I don't know if we have the time for
about 5 minutes.
In order to this 5 minutes. Okay.
Yes.
That's right. Okay. Now here we want to discuss a little about some generalization of this work. The following are classical results in higher dimensions. So let G be a reductive group, and let's mat cal X be the Bruhat-Tits tree defined from G and the complete field K. In this work, Christopher Soulet described the structure of the quotient space. Since we do not have a tree, we have a cellular complex whose dimension is bigger than 1. And Soulet described the action of the polynomial points of the preceding reductive group when this group acts on the associated Bruhat-Tits field. Just in the context where G is split. So he also described the associated amalgamated product from the preceding action, and he gives an invariant theorem for the homology of the preceding group. Okay. Then Margot, Benedictus Margot, he extends the Soulet's theorem, replacing the condition split on the group by isotrivial. This is the same that the group is split by passing to an isotrivial extension, to an manifestation of the ground field. And finally, in the context where F is finite, one of the strongest result that we know is due by Books, Cole and Bitzel in this paper, and it exposed some covering of the preceding quotient space, but here for arbitrary reductive groups. This is very important. This is totally general. In the context of quasi-split group with Luis Arenas Carmona, Benoit Lecel, and Giancarlo Lupini-Arteche, we extend the Serre's results to the special unitary group of split rank 1, which is the smallest quasi-split non-split reductive group. And since here the group is non-split, this work is does not contain in the preceding set of papers. And also with Benoit Lecel, who is a professor at the École Normale Supérieure de Lyon, we are studying the structure of the quotient space defined by the R point. Here, the ring R is arbitrary. It can be the polynomial ring or not. And this group acts on the associated Bruhat-Tits building. We study this action when G is split, and more specifically, we describe the injection of some sector faces in the quotient, also the combinatorial structure of the quotient, and then we describe the amalgamated product defined from the action, and we finally describe the set of maximal unipotent subgroup in subgroup of this group of R points. So we have this generalization to higher subgroup. And now we hope to develop the following works with Auguste Hebert, Diego Izquierdo, and Benoit Lecel. We want to study the relation between the cohomology dimension of group of this form, the group of the form G of OS, where OS is the set of functions that are regular outside a finite set S. Here S has cardinality, has a finite cardinality, but it is possible that it fails to be one. And we want to do this description on the cohomology dimension by describing the associated quotient spaces. We have some example in the context of SLM, and also in the product of trees, I think, but this is a working process. Also, we want to generalize work due to the existence of some continued fraction defined from the action of GL2R. Indeed, the polynomial ring here, the polynomial, the section of GL2 by the polynomial ring. This is the work of Polan, and we want to extend this to a certain discrete subgroup of GL2K, also approximated all the elements in K. And this is a work in process with Luis Arenas Carmona. So they are the further developments of this type of problems. And here we have the bibliography. So this is the stronger result that we know. Here we have the work of Margot Mason. Mason describe an action, describe a quotient, similar quotient than the Serre's quotient. We have the Nagao, Polan results, something like this. So thank you very much. Thank you very much for your time, for the invitation. Thanks.
I thank you for the talk, Claudio. Do we have any questions from the audience? Oh yeah, Florian would like to ask.
Well, it's not so much a question as a remark. I can think of a nice application of your work. Specifically, I think you've got a description of the abelianization of the Hecke subgroup and also of the cusp number, I believe. And that's enough to give a dimension formula for spaces of Drinfeld modular forms. Are you aware of these things?
I really actually I am not an expert on the associated modular forms, but I know that since my PhD advisor says me that this type of theory exists, I know that there exists a generalization of the modular forms to the Bruhat-Tits tree, defined as some maps to the Hecke Congruence group or some group like this to some points at or some vertices in the Bruhat-Tits tree. I know that this type of thing exists, but I'm not an expert. I think that Mason has some works in this direction, but I can say that this is a future objective in order to study some other things. But this is very, very interesting, I think.
So yeah, I've pasted something into the chat. It's a paper by Gekela and Bass-Serre, which is from a while back. And if you look at sections 2.10 and 3.1, he basically writes down, says, well, there are these things as spaces of Drinfeld modular forms. And you can work out the dimension of these things, which is something that people are actually interested in terms of the genus of a certain modular form, but that is just the free rank of the abelianization of this Hecke Congruence group, as well as the cusp number. So I think your results can be applied almost immediately to this problem, and people will be interested in that. So you may have a look.
Well, that sounds like a free paper.
It sounds very nice.
So can you download it from there, or shall I just email it to you? I've pasted the file into the chat. Maybe you can download it straight from there.
The Drinfeld upper.
Yeah, that's right. So it's the. I'm not going to go into the details. I can't even remember all of the details now. I just remember that this sort of